Hi, I am Sanjay Patel. In this video, first we are going to derive the D'Alembert ratio test and then we'll prove its limit form, which is also known as the practical ratio test. So let us begin this result. It's a very important theorem to prove the convergence of given series of positive terms. So if, let me write this, let sigma n, let sigma n is equal to 1 to infinity be a series of positive terms, Okay. If there exists some positive integer, say m belongs to n, such that number 1, for every n greater than or equal to m implies the ratio of two successive terms, so any term divided by the previous term, is less than some constant r, okay, where the constant r is 0 less than r less than 1, okay, r is positive constant lying between 0 and 1, then sigma n is equal to 1 to infinity is convergent series, Okay. And secondly, if for every n greater than or equal to m, if we have an plus 1 upon an, this ratio is strictly greater than 1, then the series sigma an is divergent. So this result is known as D'Alembert's ratio test. Let us prove this. So proof of this, there are two parts here. In the first part, what is given is for every n greater than or equal to m, there is some positive integer m such that this condition is satisfied for some value of r between 0 and 1. Okay, so we can also say that an plus 1 upon n is less than r and r is less than 1. Okay, so the first part, here the given series is sigma n is equal to 1 to infinity. I start with this from hypothesis. From the hypothesis, we have, say, for every n greater than or equal to m implies an plus 1 upon an is less than r. Okay, so this we can rewrite as an plus 1 is less than r times an. Remember that all the terms of this series are positive, so there is no harm in multiplying both the sides by some positive number in this inequality. So if I put n is equal to m here, what I will get is am plus 1 is less than r into am. For n is equal to m plus 1, this is true for every n greater than or equal to m. So we can put n equal to m plus 1, m plus 2, and so on. So putting m plus 1, what we get is am plus 2 is less than r times am plus 1. Okay, but r times am plus 1, this is less than r into ram, because this am plus 1 is less than r times am. So I am replacing this am plus 1 by this previous inequality. So this is equal to r square into am. So what we have proved is am plus 2 is less than r square into am. Okay. Similarly, if I put m is here, n is equal to m plus 2, what I will get is am plus 3 is less than is less than r into am plus 2. But am plus 2 is less than r square into am. So this is less than r into r square into am. So that implies what we get is am plus 3 is less than r cube into am. So this way we can write in general form that so in general, let me write this way. So in general, we have am plus k is less than r raised to k into am for every k is equal to 1, 2, 3 and so on. Okay. So now what I want to do is I want to consider the series sigma, say n is equal to m to infinity an. Okay, sigma n is equal to m to infinity an. That is am plus 1 plus am plus 2 and so on. Now for this series, the sum of the first n terms, suppose if I denote it by say Sn, the sum of the first n terms, of this sigma m to infinity an, okay, is given by say Sn is equal to am plus 1 plus am plus 2 plus and so on plus am plus n minus 1. We want to write down the sum of the n terms, first n terms. It starts from n equal to m. So first term is am, next term is am plus 1 and so on. Now we have already proved that all this am plus 1, am etc. all satisfy this condition. Let me write this as result number 1. So from 1 we can say that this I am keeping as it is. This is less than am plus 1. See, we already proved here am plus 1 is less than r times am. So that I am writing here am plus 1, keeping the first term as it is. This is less than r into am. Am plus 2 is less than r square into am. Then r cube into am, we will get r cube into am plus and so on plus, where it is am plus 2, it is square here. If am plus 1, we have r raised to 1. For am plus 3, we have r cube. So for am plus n minus 1, we have r raised to n minus 1 into am. So this sum is less than this thing because of result number 1. Okay, what is the result number 1? This is the general form here, which we have derived from this our observation. Okay, now from this, what we can write is taking am common. Okay, what I will get is 1 plus r square and so on up to r raised to n minus 1. So this is clearly a geometric series, and we want to find the sum of the first n terms of the geometric series with the first term as a is equal to 1 and the common ratio is r. R square upon r is r cube upon r square is r and so on. So the sum of this series is given by a into, that is 1 minus say r raised to number of terms, that is n, upon 1 minus r, okay, because it's a geometric series, and with a is equal to 1 and the common ratio is r. Okay, r is the common ratio. Okay, so what I can now write here is this. You just observe that we have started with Sn and we have proved that Sn is strictly less than this number. So let me reiterate that. So thus Sn is less than am into 1 minus r raised to n upon 1 minus r. Okay, See now, what is R? We have R is a number between 0 and 1. If 0 less than or less than 1, then we know that this R raised to n is say always less than R. R raised to n is always less than R. It is very easy to understand. Suppose if you take any number, say R is equal to 0.1, between 0 and 1, and if you find R square, it is 0.01, then R cube, it is 0.001, and so on. So R is greater than R square is greater than R cube, and so on. Okay, so if you keep on taking the power of R, which is lying between 0 and 1, for any number between 0 and 1, if you take the higher powers, the value of the number becomes smaller. So R raised to n is less than R. Okay, and so it is also less than 1. So R raised to n is less than 1 because R is less than 1, and R is positive. So this is also greater than 0. And for such a number, we can say that 1 minus R raised to n, okay, means this number R raised to n is less than 1. So if we remove some positive quantity from 1, which is between 0 and 1, and this value is less than 1. So what I can do now is I can replace the numerator by this inequality, that is less than 1. So from this, let us call this as 2. So from result 2, what I will get is Sn is less than Am, which is in 1 minus R raised to n upon 1 minus R. Now I can write this less than Am into 1 upon 1 minus R, okay, because of this inequality. 1 minus R raised to n is less than this. Now R is a fixed number. 1 minus R is also some constant, and Am is positive. So this is some positive number, and what we have proved is that 0 less than Sn is less than this constant Am upon 1 minus R. Sn is positive because all terms of the series are positive, so Sn is positive. And that means the sequence Sn is bounded above. Sequence Sn is bounded above. Okay. Also, since all terms of the series sigma an are positive, this Sn is increasing sequence is clear because S1 is only Am, S2 is Am plus 1, and so on. So when you find say S1, S2, S3, and so on, you will get say larger and larger values. So it is also clear. It is also clear from our series that S1 is less than S2, S2 is less than S3, and so on. So that is Sn is increasing sequence. Sn is increasing sequence. Sn is bounded above and it is increasing, and therefore the conclusion is therefore limit n tends to infinity, Sn exists. This limit exists by a theorem about monotonic bounded sequence, which we have mentioned in our first video, that every bounded sequence which is monotonically increasing or decreasing is always convergent. So Sn we have proved it is bounded above and also it is increasing, therefore its limit must exist. Okay, and if limit of Sn exists, and that implies the corresponding series. That implies the corresponding series. What is the corresponding series of Sn? Sn is this. Okay, so corresponding series we have taken is sigma m to infinity. This Sn is the sum of the first n terms of sigma an. Let me write here n. Some of the first n terms of sigma an. So sigma an m to infinity is convergent. So therefore sigma n is equal to m to infinity an is convergent series. And again, if you add or remove some finite number of terms from a given series, its convergence is not affected. That also we have proved. So if sigma m to infinity n is convergent, then sigma say n is equal to 1 to infinity an is also convergent. Is also convergent. Okay. So we have proved the first part, that if the ratio an plus 1 upon an is less than r, where r is between 0 and 1, then sigma n is convergent. Okay. Now let us prove the second part. What is the second part? If for some positive integer m, if this ratio is greater than 1, okay, then sigma n is divergent. Okay. So the second part is as follows. Now suppose an plus 1 upon an is greater than 1 for every n greater than or equal to m. Okay. So that gives us for every n greater than or equal to m, I can write an plus 1 is greater than an. Okay, remember all ans are positive, and therefore if I put n equal to m, what I will get is am plus 1 is greater than am. Then for n is equal to m plus 1, so am plus 2 is greater than am plus 1. Okay, and for n equal to m plus 3, what we will get, am plus 3 is greater than am plus 2. Okay, so this gives us am plus 2 is greater than am, because this am plus 1 is greater than am. Same way, am plus 3 is greater than am plus 2, and am plus 2 is greater than am. So this implies I can write am plus 3 is greater than am. So this way, if we continue, then we can write in general form. Therefore, in general, what we can write, the am plus 1 is greater than am plus 2 is greater than am plus 3 is greater than am. So in general, am plus k is greater than am for every k is equal to 1, 2, 3 and so on. Okay, for every k is equal to 1, 2, 3 and so on. Fine. So if this is the case, if all terms of a sequence are greater than am, then we can say that the limit as k tends to infinity of this am plus k is greater than or equal to this number, is greater than or equal to am. Okay. Or let me, if we take k tends to infinity on both the sides, then also there is no problem, because what we'll get is this is equal to am. Okay. And that means limit k tends to infinity, am plus k is strictly greater than 0. So it is not equal to 0, because this limit is greater than or equal to this number which is positive. This number am is strictly greater than 0. So this limit is not 0. And this limit is not 0 if the limit of the nth term of sigma m to infinity. So I can say that this implies the series sigma am plus k is equal to 1 to infinity is not convergent, that is divergent. Okay, by the first condition, that if sigma n is convergent, the limit n tends to infinity n is equal to 0. If limit n tends to infinity n is not equal to 0, then sigma n is divergent. So we are using that first basic theorem, and this means we can also write sigma n is equal to m to infinity. Yes, n is equal to m plus 1 to infinity, rather m plus 1 to infinity an is divergent. We can also write in this form. Okay, so if you put n is equal to m plus 1, you will get the first term am plus 1, then am plus 2. Here also if you put k is equal to 1, 2, 3 and so on, so am plus 1, am plus 2 and so on. So that means the conclusion from this I can write as sigma n is equal to 1 to infinity an is also divergent. Addition or omission of some number of terms from a given series will not affect the convergence. So sigma an is also divergent. So we have proved that if the ratio an plus 1 upon an is greater than 1, then the series sigma an is divergent. Okay, so this proves the theorem. So hence the theorem is proved. Hence the theorem is proved. Now we are going to prove the limit form of this ratio test, which is also known as practical ratio test. Very useful for solving problems. So next useful result is known as practical ratio test. Practical ratio test, or say limit form of the Alembert ratio test. Alembert's ratio test. Okay. Now what is this? Say, suppose we have sigma an. N is equal to 1 to infinity. Be a given series of positive terms. A series of positive terms. And suppose the limit of the ratio an plus 1 upon an as n tends to infinity, this limit exists and is equal to say L. Suppose this limit exists. Okay. Then prove that number one, the first thing, if L is less than 1, then sigma an is convergent series. Number two, if L is greater than 1, then sigma an is divergent. But if the value of the limit is 1, if L is equal to 1, then we cannot say anything. That means the test fails in this case. The test fails. Okay. Means it can be divergent or it can be convergent. So we cannot determine the convergence when L is equal to 1. And that will explain by examples after proving the first two, say, results. Okay. So let us prove. First case, here we are given that L is less than 1, and note that all an are positive here, and therefore the limit n tends to infinity, an plus 1 upon an. So these terms are also positive. So the limit of a sequence of positive numbers is always say positive. Okay, it's always positive. It can be greater than or equal to 0. Okay. So what I want to do here is, this L is lying between 0 and 1. L is lying between 0 and 1. So let me show you this way. Consider a number line. So on this real line, we have 0 somewhere here, 1 is somewhere here, and the number L is lying between these two somewhere. So L is, say, here. First, I will choose another number R, okay, which is between 0 and 1, such that L is less than R. Between L and 1, there are infinitely many numbers, so I can choose a number small r such that 0 less than L less than R less than 1. Okay. So as let me write this. Choose a number 0 less than r less than 1 such that this L is strictly less than r. And as L is less than r, we can say that r minus L is greater than 0. Okay. Now we are given that limit n tends to infinity. This limit exists. Limit n tends to infinity, an plus 1 upon an is equal to L exists. This is given. So by definition of limit of sequence, for every epsilon greater than 0, there exists some integer m such that for every n greater than or equal to m, mod of an plus 1 upon an minus L is less than epsilon. So just applying the definition, and for every epsilon that positive integer m you can find, and here I want to take my epsilon as this positive number. So taking epsilon is equal to r minus L, which is positive, there exists some positive integer, there exists some m belongs to n such that for every n greater than or equal to m implies mod of an plus 1 upon an minus L is less than epsilon. This is what I am doing, is I am applying the definition of limit of a sequence. Limit n tends to infinity xn is equal to x means for every epsilon we can always find some m belongs to n such that whenever n is greater than or equal to m implies mod of xn minus x is less than epsilon. Here this xn is this sequence, that is an plus 1 upon an, okay, and this x is the limit L, and this epsilon, which is arbitrary, I am taking as r minus L, which is a positive real number. So we can write down this statement. Okay. Now removing this modulus, what we can write here is, therefore, for every n greater than or equal to m implies L minus epsilon less than an plus 1 upon an is less than L plus epsilon. So here a less than b less than c, everything is true for all values of n greater than or equal to m. So in particular, I want only this much, which is also true. So therefore, for every n greater than or equal to m implies I can write an plus 1 upon an is less than L plus epsilon. But what is L plus epsilon? That we can write from this definition of our epsilon, which we have taken as r minus L. So L plus epsilon is r. So this is equal to r because epsilon is equal to r minus L. Okay. So this implies what we are getting is an plus 1 upon an is less than r. And what is r? R is less than 1 because our r is lying between 0 and 1. 0 is less than r is less than 1. So this says that our series satisfies this condition of the ratio test what we have proved in our previous theorem. So we can write the conclusion. Therefore, by the ratio test, sigma n equal to 1 to infinity is convergent. So in this case, the theorem is proved. Okay. Now let us consider the second part. In the second part, what we are given is L is greater than 1. Okay. So suppose L, the limit L is greater than 1. Okay. So therefore, you can say L minus 1 is positive. So L minus 1 is positive. Now we have limit n tends to infinity an plus 1 upon an, and that is equal to L. So again I will apply the definition of limit of sequence, what we have understood here. That definition of limit of sequence we are applying for xn is equal to this sequence, x is equal to L, and I will take epsilon is equal to L minus 1. So what we can write next is, therefore, for epsilon is equal to L minus 1 greater than 0, we can find some positive integer m such that for every n greater than or equal to m implies mod of an plus 1 upon an minus L is less than epsilon. So that I can write as L minus epsilon less than an plus 1 upon an is less than L plus epsilon. Now here also we have A less than B less than C is true. So I want only the first part here, that is this one. Okay. So what I'm going to do next is consider only the first inequality, and we can write this from this L minus epsilon is less than an plus 1 upon an. But what is L minus epsilon? From this, our definition of epsilon, L minus epsilon, taking epsilon on this side and 1 on this side, L minus epsilon is 1. So this is equal to 1. This is equal to 1. Okay. So because epsilon is equal to L minus 1. Okay. And therefore L minus epsilon is 1. So that is, I can say an plus 1 upon an is greater than 1. 1 is less than this means n plus 1 upon n is greater than 1 for every n greater than or equal to m. And again, by the ratio test, what we have proved in the previous theorem, again by the ratio test, sigma n will be divergent in this case, is divergent. Okay. So we have proved the theorem. If limit n tends to infinity, an plus 1 upon an is equal to L exists, then for L less than 1 it is convergent, the sigma n is convergent, for L greater than 1 it is divergent. Now the third part of this theorem, that is we want to show that the test fails for the case L is equal to 1. To show that for L is equal to 1, the test fails. For L is equal to 1, then the test fails. So what I will do is I will consider two series, okay, and in for both the series we'll find the limit of an plus 1 upon an, and the limit L will be 1 in that case, and we show that one is convergent, other is divergent. That means we cannot determine the convergence when the limit value of that ratio sequence is 1. Okay, so let us consider two different examples. So first example here is consider the series sigma n is equal to 1 to infinity as sigma 1 upon n square, where n is equal to 1 to infinity. Okay, so what is an? An is 1 upon n square. Okay, so what is an plus 1? So n plus 1 is 1 upon n plus 1 square. Okay, and therefore if I find the limit of an plus 1 upon n, so limit of the ratio sequence an plus 1 upon an, what you will get is limit n tends to infinity an plus 1, that is 1 upon n plus 1 square and n square. So what you will get is, I am writing directly, n square upon n plus 1 square. And you know how to find this limit? Dividing by the highest power of n, every term in the numerator as well as the denominator. So n square upon n square is 1. Here also I am dividing by n square. So that n square we can take inside and we will get n plus 1 upon n whole square. Or we can write this way also. This is equal to limit n tends to infinity, okay, 1 upon 1 plus 1 upon n whole square. And this tends to, as n tends to infinity, 1 upon n tends to 0. So this tends to 0. So 1 upon 1 plus 0 square, and that is 1. So L is equal to 1 in this case. Okay, L is equal to 1. And also we can note one thing. The series sigma 1 upon n square is a p series, okay, and therefore it is convergent. The series is convergent because we have p is equal to 2 here and it is greater than 1. So this is p series. So this series is convergent and the value of the limit L is 1. So that is the first thing. Now we'll show the another example in which limit is 1 but the series is divergent. So consider the second problem. Consider the series sigma, say an is equal to sigma 1 upon n, 1 to infinity. Okay, and as p is equal to 1, it is a p series, so p is equal to 1 here. So I can say that sigma 1 upon n is divergent. So this is my first observation. Now about the limit of the ratio. Now limit n tends to infinity, n tends to infinity, an plus 1 upon an is equal to limit n tends to infinity. What is n plus 1? An is 1 upon n here. From this given series, we can say n is 1 upon n. So n plus 1 is 1 upon n plus 1. So 1 upon n plus 1, okay, 1 upon n plus 1 divided by an. What is an? It is 1 upon n. So this is equal to limit n tends to infinity, n upon n plus 1. Okay, that is nothing but limit n tends to infinity, 1 upon 1 plus 1 upon n, dividing every term in the numerator and denominator by n. And therefore this tends to 1 upon 1 plus 0, which is 1. So again the limit is 1. So what is the conclusion? Here the series sigma 1 upon n is divergent, but the limit is 1. Okay. So the conclusion is this. Therefore, sigma 1 upon n square, or sigma an, let me write, sigma an, that is sigma 1 upon n square, is divergent. Okay. And L is equal to 1. So from these two examples, in first example, we have taken sigma 1 upon n square, and for that the limit of the ratio n plus 1 upon n is 1 and the series is convergent. In the second example, we have shown that limit of the ratio is 1 and the series sigma 1 upon n is divergent. So one cannot decide when the limit value turns out to be 1. So the conclusion is thus if L is equal to 1, then the test fails. Then the test fails from example 1 and 2. So from 1 and 2, we can say this. So this proves the practical ratio test, okay, or it is also called limit form of the ratio test. Let us go back and understand the statement. It is important. Given a series of positive terms, if you want to determine the convergence, so first find the ratio an plus 1 upon n, find out the nth term an, find the ratio an plus 1 upon n, take the limit, and suppose the limit exists and it is L, and the value of L is less than 1, you can say immediately sigma n is convergent. If L is greater than 1, then sigma n is divergent. Okay, but for L equal to 1, we cannot say anything. It can be convergent or divergent, so nothing can be said. Okay. And remember, this theorem is true only when this limit exists and it is some real number. Okay. And if limit does not exist, then also there are many other tests which we'll study in the analysis course. Okay. So we stop here in this lecture, and the next lecture we are going to take some examples of say convergent series using the Alembert ratio test. Okay. Thank you.